Hi, this is John Isles and welcome to Geometer's Paradise. Today we're going to be talking about Lesson 3 in Unit 7, this one about medians and altitudes of triangles. We have several goals in the lesson, the first of which is that as the culmination of kind of a three-lesson arc, students will be able to identify perpendicular bisectors, angle bisectors, medians, and altitudes from a selection of given information. Students will also be able to use the centroid, which we're going to learn about today, to make calculations, and to identify the orthocenter of a triangle. If you just give me a second here, my tablet has closed down. Alright, very good. Okay, the first thing that we want to do today is define median. A median is a line segment that's drawn from a vertex of a triangle through the midpoint of the opposite side. So that this segment here from C, from C to the midpoint, we'll call this M, and B to the midpoint are equal, and then AM is called a median. Alright, so you might say this, if you were writing a proof, you might say CM is congruent to MB because AM is a median. Okay. Alright, it turns out that just like the perpendicular bisectors and the angle bisectors, that the medians are also concurrent. That means that if I draw all three medians from A, from C, and from B, they will intersect at one point. And this one is a very special point. This point is called a centroid. So let's call this M, and it's called a centroid. Now, the reason for this, if you do a little etymological work, you find out that the suffix oid means similar. Okay, and this is significant because each median is cut by the centroid into a piece that's exactly half the length of the other piece. For example, this piece X would be 2X over here. And if this were Y, this would be 2Y. And if this were Z, this would be 2Z. Okay? To verify it, we can draw a circle from the centroid. Alright, so there it is. Okay, now the fact that it touches down here, that's coincidental. What we want to focus on is that if I draw another circle from this point to the center, you see, 1, 2, 3 congruent pieces. So Z, and then this piece, and this piece, all the same. So in fact, the short piece relates to the entire median in a 3-to-1 relationship, while it relates to the longer piece in a 2-to-1 relationship. Okay? And I think I have another slide for all this, but whatever, I'm just going to keep going here. So the shorter piece, okay, times 2 is equal to the longer piece. Okay, and the shorter piece times 3 is equal to the whole median. Now, if I do a little fancy math, I'm going to change these around. I'm going to say 2s for short is equal to L, and 3s is equal to M. So what I'm going to do is I'm going to divide this one. I'm going to say s is equal to M over 3. Okay, and then by substitution, 2 times M over 3 is equal to L. This means that 2/3 the length of the median is equal to the long piece. So the ratio of the median to the longer segment is 2/3. The ratio of the short piece to the longer is 1 to 2, and the relationship of the short piece to the entire median is 1 to 3. And you're going to use this to make all of your calculations in class. Okay, so that was a lot of info. Let's do an example. I'm going to use this slide to do an example. Let's suppose here we have AX and here's CY, and that's all I'm going to draw for right now. Let's see, pen, there we are. Let's call this X, let's call this Y, let's call this centroid here M. So this point here is the centroid. So let's suppose that MX is 4. Okay, if MX is 4, that means that AM is going to be 4 times 2, which is 8 units. And that AX, the entire segment, is going to be 4 times 3, which is 12 units. Okay. Now let's suppose, on the other hand, that CM had a value of, I don't know, let's go with 9. If CM is 9, then MY is going to be 1/2 times 9, or 4.5. Because remember, this is a 1 to 2, so this is doubled. I'm going to halve it to get MY. So that's 4.5. Then I can calculate CY by taking 4.5 times 3, and that would do it. So this is 15, 13 and a half. Okay. All right. So that's how you would do those calculations again. So this down here, this ends up being 4.5, and the entire thing is 13.5 units. Now, this is supposed to be a proof of it. We don't actually, we can't actually do the proof until much later, and the way you end up doing it is with similar triangles. So we don't have the ability to do similar triangles just yet. But when we do, the relationship is going to be very, very clear. And so we'll come back to this proof middle to end of chapter or unit. It'll be unit 8 for us. Okay, altitudes. We've worked with altitudes before many times, and an altitude is just a line segment that's drawn from a vertex and perpendicular to the opposite side. So that's one thing that we want to remember about altitudes, is that we're always perpendicular. Okay, and it turns out that if we draw the altitudes from each point in a triangle, that they are going to end up being concurrent, just like everything else that we've studied so far. The thing about it is, though, that the concurrency of the altitudes produces a result that does not have any immediate or algebraic impact on us. However, if the angles are acute, it does have one interesting property, and that the altitude creates a triangle inside. So if we were to take this and draw a triangle by connecting the line segments, so if I were to go from the feet of the altitudes and I were to draw a triangle, then allegedly, I don't have a proof for this, I just read it on the internet, so you can't believe everything you read on the internet, but allegedly this triangle is the triangle with the shortest perimeter, meaning that if I were to walk around it, this triangle is the shortest perimeter of any other triangle that you can draw that touches all three sides. I don't know. Aside from that, I haven't seen a logical use for the orthocenter or a mathematical function of it, but it does exist. So, in a review here, oh, that's bright. Okay, in a review here, we've learned about perpendicular bisectors. Okay, perpendicular bisectors. And perpendicular bisectors are concurrent at a point called the circumcenter. Circum is a prefix in this case that means around. Okay, so this is around, and if we use the circumcenter, we can draw a circle around the triangle that we're working with. We also talked about the angle bisectors of a triangle, and we learned that the angle bisectors are concurrent at a point, and that point is called the incenter. And it's called this because if we use the incenter, we can draw a circle inside of the triangle and tangent to all the sides. We'll learn about tangent clear down the road in semester 2. We also just today learned about medians, and the medians are concurrent at a point called the centroid. Okay, OID meaning similar, and the centroid divides each median into a 1 to 2 relationship. And finally, we talked about altitudes, and the altitudes point is called the orthocenter. And I haven't looked this up yet. Give me just 1 second. Let's see what Google thinks of the word ortho. Okay, it means straight, upright, right, or correct. So I don't know, take your pick. The orthocenter is the one that doesn't seem to make a whole lot of sense in the world of math, but it's part of our studies, so we include it. Okay, that's going to be it, and have a good day.